So all of this looks like very interesting functionality. We'll look at how you would implement something of that in the hardware. Now there are a couple of things that I am going to sort of just highlight before we go in and actually look at the Verilog code itself, right. The first is similar to what we already saw in the case of the AXI-lite register bank, right. We sort of take out the addresses that we are interested in. We are doing a word aligned map, meaning that our addresses are automatically going to be 0x00, 04, 08, 0C, and we are essentially going to say that we are to avoid any chance that even by accident I give the address 1 or 2 or 3, right, because if I give the address 1 or 2 or 3, they all actually correspond to the word starting at address 0. Only after 4, then 4, 5, 6, 7 correspond to this one. Now that can get confusing because you might actually want to read one particular byte at location number 3, right, but as far as the entire decoding procedure is concerned, that can get a bit tricky. So what we say is we are not going to allow that kind of functionality. For now we just say that even in the Verilog itself, we will only look at address of 3:2. The bottom 2 bits 1 and 0 are just going to be ignored. What that means is the numbers 0, 1, 2 and 3 all look like 0, 4, 5, 6, 7 all look like 4, 8, 9, 10, 11 look like 8 and so on, right. I am just masking off the bottom 2 bits. Now why do I do this? This effectively gives me something called register aliasing. Multiple addresses are decoded into the same location, right. This can potentially cause confusion because from the software point of view, I can give an address either as 0 or as 1, right. In the hardware, if we sort of say, so then comes the question of should I sort of use some kind of bit masking or byte masking or shifting things around in order to decide whether I should write a value into this location or not. This is taking a simpler approach. It says, look, that's a software problem. If you want to write something into a particular byte, you figure out which byte you want to write into and give me that information explicitly. Don't expect the hardware to sort of move things around and get them into the correct location, simply because it complicates the hardware a bit more than you would like, which in turn hits things like your critical path, right, which would directly impact the speed at which your circuit can work. Instead of that, it's unlikely that this is a very common occurrence that you need to set one particular byte. Well, you might as well set all 4 bytes of them at once, right. You don't really gain anything by trying to set only one byte. So you avoid this confusion in the hardware and enforce word level access by basically masking out the bottom 2 bits. And more than that, let us say that within the 4 byte value of this address 00, for example, if I want to write only into the 0th byte, that is to say one of the 4 bytes, then I can use something called the strobe signal. We looked at this briefly in the register bank definition. The strobe signal is a 4-bit value which indicates which of the 4 bytes in my system should actually be written to. And in this case, it essentially allows me to write code that would impact just one of the 4 bytes corresponding to the system. Now typically it would probably be easier to just say write all 4 bytes and then make sure that you handle it appropriately in software. The common approach would be you read a value from the register, you mask off everything that you don't want to change and only change the bits that you are interested in changing and write them back. So the byte enables are essentially what are captured in this W strobe signal, right. And like I said, the way that would get implemented in Verilog would be, well, you can write it as a for loop. This kind of a for loop essentially would expand out, even though it writes for loop out here. Data width is 32 bits, so 32 by 8 is going to be 4. This for loop needs to run 4 times. Now in hardware, things don't run one after the other, especially when you write a for loop like this. Even if you want to sort of create something which takes multiple cycles, then you have to write a finite state machine. You can't just write a for loop. So what does this get converted into in hardware? 4 copies of this statement, right. The first copy says if W strobe Q of 0 is 1, right, then the period shadow, remember what I said about shadow registers, we are going to write data only into the shadow registers. The period shadow of 0 to 8, right, or 0 to 7 basically, is going to get the value from W data queue of 0 to 8 or 0 to 7. This notation plus colon 8 says 0 to whatever is required in order to get 8 bits further from there. If WSTRB queue of 1 was equal to 1, then period shadow of 8 to 15 would get the value W data of 8 to 15 and so on, right. So, it basically expands out into 4 copies of this particular statement that we would get in order to do. We can actually use that to do partial software writes. I can by controlling WSTRB, I can decide that instead of writing all 4 bytes over there, maybe only 1 or 2 or 3 or all 4 get written. In general, we need to document which of the bytes matter, and as we will see, the control register actually uses only byte number 0, right. But at the same time, because of the fact that other writes to other locations are ignored, it does not really matter whether or not we use the WSTRB. As I said, we will also be using something called a self-clearing pulse, right. And the way that a self-clearing pulse gets implemented in hardware is, the Verilog code would look something like this. You essentially set the control pulse by default equal to 0 inside some always block, and then you have a condition which checks if this WSTRB queue is equal to 0, that is to say you are trying to write into one particular location, and if the address, it also needs to check the address and say that the address corresponds to the control register which is 0 0. If so, then the control reset pulse will become equal to W data queue of 1. What does that mean? It basically means that this control reset pulse, if I write 1 into the location W data queue of 1, then control reset pulse will become equal to 1. The interesting thing is, because of this statement out here, which is outside of the case statement and outside of this if statement, right, the next time I come through the always block, in other words on the next clock cycle, control reset pulse will get set back to 0. Control enable on the other hand will remain as 1, because I do not have a default condition of control enable equal to 0. Control enable will be assigned a value out here, it will get the value whatever is in W data queue of 0. It will retain that value until I write 0 into W data queue of 0. Okay. And effectively a write 1 to pulse will make the signal, right, will make that pulse, the reset signal just go high for one clock cycle. It is used for what are called actions. I just want a very specific reset action. Enable on the other hand is not an action, it is a state of the system. Is the counter enabled? That is part of the state of the system, right. So, that cannot be a pulsed signal. What we typically use it for is this kind of soft reset, that is a software control reset, or for starting certain kind of capture, or for a watchdog timer, because watchdog timers also work in this way. I typically need to at regular intervals go and, well, as I say, kick the watchdog, right, and what that means is just write 1 to a particular location. It is not that that 1 is going to get stored over there, it will just pulse, that value will go back to 0, but at least it has now reset whatever conditions were going to trigger the watchdog timer inside the system, and it starts counting again from 0, right. Now, when we read back the data, this reset pulse should not get latched anywhere inside the system. When I read back a value, it should just return a 0 corresponding to the pulse bit, right. The interesting thing of course is what you read back versus what you wrote may not have any connection as such, right, because as we saw in the register bank already, the W data is coming in from the right part of the AXI bus, the R data is what is going back, and how you decide what to put in R data versus what came in from W data may be completely different. Now, one more thing that can be done is, as I said, the write 1 to clear, right. We have the status bit which is set based on an event that happens somewhere, right. So, I have some condition inside, remember that all of these things where since status wrap is some kind of a registered signal, it will have to be inside an always block inside Verilog, and what that means is I cannot actually set values to it inside 2 different always blocks. That will not synthesize properly and you will probably get some complaint about multiple drivers and so on, and the system will fail to synthesize the way that you expect. So, what I am describing over here, as we will see later, is that both of these conditions happen inside the same always block, and within that always block you would have one condition which checks whether the wrap pulse has occurred, in which case I said status wrap equal to 1, and another condition which checks, am I actually writing into bit number 0, WSTRB Q of 0, that is to say I am actually trying to write into the byte number 0, and within that I have bit number 0 equal to 1. If so, clear the status wrap, because I wrote 1 into it, but I am actually trying to clear it, right. So, the interesting thing about this is I do not need to check whether the status signal was 1 or 0, it just forces it to 0. If it was already 0, it is fine, it will remain as 0. It does not matter if something else happened. So, this write 1 to clear is a robust way of doing it. It says I do not really care what the present state is, I know that I want to clear the value of status flag. And the other way of doing it would sometimes be that you can also implement something called a read to clear, right. And read to clear essentially says something very similar. It says that I do not even need to write anything into the register. If I even just try reading from the register, it should clear the value of a bit. Now, there are places where this is actually useful. Very often this is done, for example, with the overflow condition in some ALU status flags, right, where you might find that the ALU sets a particular overflow or arithmetic error or something of that sort, some kind of flag like that is set, and then I can check branch not 0 or branch on error or branch on flag, right. And as soon as I do that branch on flag, it means I am going to read from that flag, the flag immediately gets cleared as soon as I look at it. It does not retain that status any further, right. So, that read to clear is also possible, but especially when you have a flag that could potentially be read in multiple different places in the software, that is not a good idea, because you do not know which part of the software is going to read and clear it. You would rather make the writing to clear explicit. Okay, one more thing before we get into the actual code itself, right. I mentioned this notion of shadow registers, and the idea of a shadow register is simply this: the period active is the period that I actually want to set for my PWM core, right. It should count for, let us say, up to 1000 and then go back to 0 and then start again. And as I said, if I am in the middle of a counting process, I do not want to change that period midway through, because it can actually lead to confusion. Instead of that, what I do is I check if there are any updates. If the control enable is currently high, then I just set the update value to be 1, update pending to be 1. Otherwise, I say okay fine, go ahead and update the value of period active and say that there is no update pending at this point. But on the other hand, if control enable was 1 and I set update pending equal to 1, then later after several clock cycles, I will find that update pending is 1 and the status wrap also gets set to 1. At that point, I know that the system has finally managed to wrap around, immediately go there, update the value of the active period and also clear the update pending bit, right. So, this is a bit that automatically gets cleared internally, but in the meantime you can actually even read it back and see whether there is an update pending or where is the system currently waiting, right. So, it avoids what are called mid-cycle glitches. You have some kind of thing that takes many clock cycles to finish. In the middle of that, you do not want it to suddenly change its behavior. The updates take effect at a safe boundary, that is to say, once I have wrapped around and gone back to 0, I know that it is safe to change the period and the duty cycle. And this pattern is a very useful one. It generalizes to timers, pulse width modulators, rate generators, dividers, many things that operate over multiple clock cycles. Now, on top of all this, we also need to read back the data that is there, and the read back actually looks fairly straightforward. Once again, I look only at the 2-bit 3:2 of the address, and what I say is if it is 0, then I am going to read back the control signals, right. And interestingly, what I do over here is this bit would normally have been the reset, but I am saying no, I do not want to say that you have reset or anything of that sort. I am always going to return a 0 out there. Control enable on the other hand will be returned, it will tell you whether or not the counter is currently enabled. Address 1 will give me back the shadow, address 2 will give me back rather the period, and address 2 will give me back the duty cycle. It gives the shadow registers which at some appropriate point will get updated to be the active registers. You could also choose to return the active values, it depends, I mean that is once again a choice that you have to make, right. And finally what we have is the update pending as well as the status can also be returned by reading back from these registers, right. So we have to, what we are doing over here explicitly is that many of these locations, the unused bits in many of these fields, right, the read only field, right, or the pulse bit, we want them to behave predictably. So we generally return either 0 or the current state. In this case there is no other current state, so we return 0 for the system. Now this notation RAZ or WI stands for read as 0, which in this case is that is what we are doing. We are basically saying that all of these bits, they are unused, but they will be read as 0, and any write into these bits will be ignored, hence the WI. So there are several examples of real world register maps that you can look at, but I am just sort of putting these out as references, right. I would encourage you to sort of look through some data sheets and understand a little bit more about how register maps are actually created for real hardware peripherals, right, because the best way to understand it now is to go back, look at some peripherals you might have seen in the embedded C course, try to understand what the register map of this means and what is it likely to be in the corresponding hardware, okay.